Hello, my name is Vincent Lequertier. I'm a PhD student at the Lyon University Hospital. My thesis is about artificial intelligence and healthcare, and I'm also a Free Software Foundation Europe volunteer. Today I'd like to talk about the upcoming challenges in artificial intelligence research and development, including fairness, parameters reuse, and model training. So for the first part of my talk about fairness, I'd like to introduce some vocabulary. The true positives and true negatives are where the predictions were correct, meaning that you predicted true and the observed value was true, or you predicted false and the observed value was false. False positive and false negatives are where when the predictions were incorrect. So you predicted false and the observed value was true, or the other way around. To explain the concept of fairness in algorithms, I'd like to give you a few examples. The COMPAS recidivism scoring algorithm tells if criminals are going to recidivate their crime or not in some United States courts. The problem with this algorithm is that it had different performance depending on the skin color. The algorithm often mistakenly predicted a high risk of recidivism for black people and a low risk for white people. You can see this in the false positive rate and the false negative rate. The false positive rate were almost 50% for black people, and the false negative rate was almost 50% for white people. Another example, this time in healthcare. So this is a graph summarizing the result of an algorithm predicting the risk score for patients. So the x-axis tells the risk score predicted by the algorithm, and the y-axis predicts the number of conditions of the patients. As you can see, black people had to be sicker to have the same predicted risk score as white people. So this algorithm was giving different results according to the skin color, which is unfair, obviously. So an algorithm can be unfair because it can be there can be bias in the input data itself, or it can be trained with the wrong evaluation metric, or the algorithm can be trained with the right evaluation metric, but it forgets about everything else. So it optimizes for this metric, but not for fairness, for example. Or you can have a bad prediction model that introduce unfairness. Here I'd like to introduce you to a fair loss function. A loss function is used during the training of an algorithm to tell how accurate it is, that is, how well it is performing. So according to this metric, you adjust the parameter of the model to improve its accuracy. To create a loss function that is fair, I add to this regular loss value. So this value comes from a function. This function tells if a result is fair or not from the predictions of the algorithm. So what you do is you sum the result of this function for all possible value of a protected attribute. The protected attribute is something sensitive, like the gender, the religion, the skin color, and so on. So you sum up the result of this function for all possible value of a protected attribute, you divide by the minimum, and you try to minimize this value as well as the loss, meaning that you both optimize for the accuracy of the model and for its fairness at the same time. The second part of my talk is about parameters reuse. So what are parameters? Parameters in the context of deep learning is small numbers that are added or multiplied together, and they are organized into layers, and they lead to a prediction. In real-world examples, there are millions or billions of those parameters. Reusing parameters means reusing some layers from already trained model as part of your model training, meaning that when you train your model to give accurate predictions, you reuse parameters from already successful and already trained model. So I'll give you some time to read this comic. So training a model can be really time consuming. It can take hours or days to train a large model. By reusing some already trained model and some parameters, you avoid doing some computation, which saves you a lot of time. Reusing parameters also saves a lot of energy. This table summarizes a study about the energy impact of natural language processing models. The results are in kilowatt per hour multiplied by the PUE, which is the energy impact of the data center itself, like things like cooling the machines and so on. And the results are also in carbon dioxide. And you can see that training those models takes a lot of energy. So by don't having to train them yourself, and by reusing already trained model in natural language processing, you avoid a lot of energy cost. Parameters reuse is also good for knowledge sharing. By sharing models, layers, and parameters with each other, we can leverage knowledge from multiple models as part of one model. So we share the knowledge accumulated by different models as part of a bigger one to achieve maybe greater goals. So what is needed is to make it easy to reuse parameters of models. We want to have some licensing and some platforms where we can easily share different models so that everyone can reuse them. And also, we need to find ways to reuse parameters in more domains of AI. Some part of artificial intelligence currently don't make it easy to reuse models parameters. For example, there is no way currently in reinforcement learning to reuse some already trained model as part of other models. The third part of my talk is about model training optimization. So model training optimization means optimizing the way the model is going to be trained. This is done by a process called Hyperparameters tuning. So what is Hyperparameters tuning? To explain this, I'm going to make an analogy with cake baking. So when you bake a cake, you have control over several parameters. You can control the temperature of the oven, the baking time, and the cooling time of the cake. And modifying those parameters impact the taste and thus the quality of the cake. So this is the same with models. You have a bunch of parameters, and adjusting these parameters controlled the accuracy, that is how well the model is going to perform with several parameters. So for example, here I have 3 different parameters. Kernel takes 3 possible values, C takes 10 possible values, and gamma takes 10 possible values. So now if you want to try all combination of those parameters to find the best ones, you have 300 candidates to try. That is 300 models to train. And if you want to use 10-fold cross-validation, you have 3,000 models to train to find the best combination of the hyperparameters. So this is really time-consuming and expensive. But there are several solutions. You can use something called early stopping. So if I go back to the example of the cake, if the cake is already burned, you know that there is no point in trying to increase the temperature further. You know that increasing the temperature will lead to a more burned cake, so it's pointless. So this is the same with models. You know that if the accuracy is not great, trying to increase the value of a parameter is not going to help. So you can stop and don't try to increase further this parameter. You can also try to converge towards the best solution, that is, converge towards the best combination of hyperparameters. What you do is you monitor the accuracy of the model over several tries, that is, over several candidates, and you try to find the most promising combination of hyperparameters, and you derive new candidates based on the most promising result so far. So it converges towards the best solution. What you can do also is to make the model training faster. So maybe you don't need all your data or all your the complexity of your training loop to adjust hyperparameters. So maybe you can reduce the number of epochs required to train the model, or you can maybe reduce the size of the dataset used to train the model in the context of hyperparameters tuning. That will make the model training faster, and therefore you can try more candidates, more combination of hyperparameters. So thank you for listening, and please ask any questions you may have.